hydrogen peroxide is mixed with 2-hydroxydioic acid, then cobalt dioxide. What is observed is the cobalt 2+, the pink hexaacyl cobalt ion, goes green and then returns to pink again. And the reason for this is an intermediate, which is a complex that is formed by the 2,3-dihydroxybutane dioate ion, is the intermediate, and because of the highly polarizing nature of the cobalt 3+ ion, the bonds within the 2,3-dihydroxybutane dioate ions are weakened, and this intermediate therefore breaks down. Now you can see again the transition metal is changing its oxidation state. The cobalt is becoming oxidized, and the hydrogen peroxide, the oxygen in the hydrogen peroxide, is becoming reduced because it's gone from a -1 oxidation state to -2. And at the same time, the cobalt becomes oxidized to cobalt 3+. This ion then reacts with its own ligands, the cobalt 3+, and the ligand, the 2,3-dihydroxybutane dioate. The bonds are weakened, and that therefore now gets oxidized to CO2 and methanoic formaldehyde, and the cobalt 3+ gets reduced back to cobalt 2+. Effervescence is now beginning to be observed as the butane dioate ions start to decompose to carbon dioxide. And at this point here you can see the pink cobalt being converted into the green oxidized cobalt 3+ ions. You can also clearly see effervescence is happening as carbon dioxide starts to be produced as this species here starts to break down. Notice that the green colour persists for quite a while. So this reaction was carried out at 70 degrees Celsius to overcome the initial activation enthalpy. And as the effervescence subsides, what is happening is these species here, these complex ion surrounded by 3 bidentate 2,3-dihydroxybutane dioate ions, starts to break down. So you can now see that the effervescence has subsided, and then all of a sudden, as the effervescence subsides, you can see the colour changes, these disappear, and we get the cobalt 2+ ions returning.